All right, let's just start by kind of reminding ourselves what we did last time. Because it's a lot of math, but it's not, and it's a lot of manipulations, but none of it's hard, really, right? If you just kind of think about what we did, it's really not that hard. We define a reference and a current configuration, and then we drew a bunch of vectors on there, right? No big deal. And then basically all we did was we wrote down this vector q minus x in the current configuration, which we later labeled dx, right? So we wrote down the vector q minus x in terms of things in the reference configuration, right? So u of q minus u of x plus q minus x, right? So this equation here. We just wrote that down, and then we did a Taylor series expansion about the point q equal to x, or another way to think about that is like about the dx equal to 0, right? Or rather, dx equal to 0. So, basically what we're doing is we're looking at things in a small neighborhood of the point x, right? So the approximation that we derive through the Taylor series, and I think when I first wrote this down, I missed a 1/2 right there. But it doesn't change the final answer in any way because we zeroed out those higher order terms, right? So I did put it in later, and the notes that are published on the website have the 1/2 there, but I just neglected to write it in when I was doing the derivation live, okay? But, basically, because we're investigating things in a small neighborhood of the point x, we can zero out those higher order terms and then just work through the manipulations, and then ultimately we get this equation, which is an important equation that we'll use a lot, where f, of course, is defined, f is the deformation gradient and is defined also here, right? We also saw that this thing is also the deformation gradient, right? I think I wrote it there, right, in a box. Which basically just comes from this first equation. Again, writing little x is big X plus u of x, right? And then just taking the partial derivative of both sides with respect to big X. And that's how you get that equation. All right. So again, what the deformation gradient does is it takes vectors in the reference configuration and maps them into vectors in the current configuration. And then from that, we can define basically strain, right? So we define this basically a line segment, big D big S, right? A line segment in the reference configuration, and D little s, a line segment in the current configuration. And then if we look, at this change in length of the line segments, and we squared them because we just don't want to deal with the square root sign, right? We squared them and then eventually just did some manipulations, right? Writing down this ds squared minus ds. Just did some manipulations and ultimately defined this thing right here to be 2e. And I said that later we'll see where the 2 comes from, right? Why the 2 is there. And hopefully you can see that this is a measure of strain in the sense that, strain is like a change in length over length, right? Well, this is like a change in length. It's a measure of change in length, right? In fact, if you took the square root of that, it would clearly be, the change in length. And then you have these vectors on this side, okay, of the equation, dx transpose and dx. And it's not really a legal mathematical operation to divide by a vector, right? But if you can imagine, right, dx transpose times dx is like some notion of d big S, right? Squared, we saw that here, right? Right? So this is like, so like this is kind of like some thing like, it's actually, if you worked out the additional notation, this would be a tensor itself. Because what you would have here is something like, in additional notation, you'd have d big X I times 2 E I J dx j, right? So, so if you can when they're in additional notation, you can move them around. And so if you looked at what, like dxi, dxj, that thing itself is a tensor, right? The components, they would be the ij components. You'd multiply these values, and the ij components would go into a matrix, right? Second order tensor, which we can think of like a matrix. So you can't divide a matrix. What do you do when you want to move a matrix to the other side? You multiply by its inverse, right? So if you multiplied by the inverse of this thing, right? It's sort of like a division operation, right? And so what you would end up on this side over here would be something that's like the change in length in the numerator divided by some notion of the original length in the denominator, right? So hopefully you see that's kind of intuitively a strain, right? A change in length over length, right, is a strain. And then again, we just define it to be 2e, and because these are referenced to the reference configuration, this is what we call the Lagrangian strain, or the Green strain, or the Saint Venant strain, right? This is a reference configuration. Like, that's what we get here. All right. And I mentioned we'll see where the 2 comes from later, and later is now, is today. All right. So basically, then we also went through those same manipulations in the current configuration. Referencing everything to d little x. And then define that as 2 times little e, which we call the Eulerian or the Almansi strain. And again, remember, whenever you hear Lagrangian, you always think reference configuration. Whenever you hear Eulerian, you think current configuration, right? Or deformed configuration, okay? And again, as I mentioned before, we can, there's infinite number of strain measures. We can reference them to anything. We could reference them to some intermediate configuration, or the wall over there, or whatever, right? And we'll see how that affects what our notion of stress is later, probably next class. Okay? So then I also just showed that if you linearize the Lagrangian strain or the Eulerian strain, in both cases, you get back this thing, right? Which we call the small strain. And this small strain has a geometric interpretation, and we're going to look at that now, right? All right. So, is the door locked? Somebody came in after this opens. I think it's open. All right, so let's start by having an undeformed cube. Having an undeformed cube, we'll call this length here dx1. This length here dx2. Calling it dx obviously because we're saying this is an infinitesimal cube, right? Infinitesimally small. We're going to label this point A and this point B. All right. And then what we're going to do is we're going to deform and displace that cube. So this is the same point A. Same point A. Same point B, but now they've been deformed, so we'll call them A prime, B prime, and we'll draw the rest of the cube there. And so then if we start to look, right, so our original cube was like here. And so this distance here, we'll call U1. This distance here is U2, so that's the displacement of the point A. The distance that the line segment was stretched in the x direction, so that's this distance. That is partial U1 partial x1 times dx1. The distance it was stretched here is partial U2 partial x1 dx1. So if we want to understand what the strain in the x1 direction is, then we're just going to write down our kind of definition of strain, changing length over length, right? In like the Lagrangian sense, right? So changing length over original length. So that's the line segment A, B prime minus A, B over A, B right? So we're just saying this line segment minus that line segment divided by that line segment. It's normal kind of undergraduate definition of strain, right? Well, you see that AB is also dx1. So this is also equal to AB prime, A prime, B prime minus dx1 over dx1, and that's also equal to A prime, B prime over dx1 minus 1. So let's write down what A prime, B prime is in terms of these other things that we've defined, in terms of the displacements and the dx's, right? And so A prime, B prime is equal to, right? And you know, any if you think of A prime, B prime like a vector, then you know the vector, the length of a vector is the sum of the squares of the components of the square root of the sum of the squares of the components of the vector, right? But you guys already know I don't like square roots. I don't want to carry a square root sign around everywhere. So we're going to square both sides, right? So instead of AB prime, we're going to write A prime, B prime squared. That way the right-hand side doesn't have a square root sign over it either. So that is equal to dx1 plus partial u1 partial x1 dx1 squared plus partial u2 partial x1 dx1 squared. Okay, so now what we'll do, because we wrote this ab squared, we want this equation to be ab squared, right? So we're going to rewrite, this is, I'll write it over here, ex1 squared is equal to a prime b prime over dx1. Yeah.
Shouldn't that be dx2? Like the y component of AB?
No.
No.
Mm-mm.
du2 by dx2.
No. This one?
Yeah.
No, that's right.
Aren't you measuring the strain on the dx2 side?
I'm measuring the strain, the change in length in the x in this direction. Like this direction. I understand we're only writing one component of the strain tensor. The strain tensor's got 9 components, right? So we're trying to write the change in length in the x direction. So just by definition, what is a derivative? It's the change in it's the change with respect to something, right? So what the change in u2 with respect to a change in x1. Yeah. That's right. So yeah, so now I'm not going to write out all the terms here, but understand, like, I'm squaring this, so then we just use our rules of, like, so you're going to basically have, ultimately you're going to have AB squares, right? Because you're going to take the first term times the first term, then the first term times the second term. You understand what I'm saying?
Yeah.
Let me write it this way, maybe, just to be clear. So instead of writing the square there, I'll just write it out like this. Right, and then just like if we multiplied all this out, I'm not going to do it.
How did you make the negative sign?
That's just a typo. Thank you. I'm not going to write everything out, but understand, I'm just like, if I take this term and multiply by that one, and then I'm going to have something with an AB squared in it, right? And then I'll have a 2 a prime b prime over dx, and then I'm going to have a plus 1 on the end. So yeah, so if I work everything out, well, I guess I am writing it all out. 2 Yeah, so again, multiplying this out and substituting in this thing, and then just canceling a bunch of terms, this is ultimately what you get. And then we'll also linearize everything. So the higher, like basically the higher order terms, anything with a squared in it, we're going to get rid of. The ones cancel, the twos cancel, and then ultimately you have that is the strain in the X1. So this is like the one in the total strain tensor. This is the 1-1 component of the strain tensor, right? So partial U1, partial X1, and so I only did this for one component, but you can make these same geometric arguments for all of the strains, right? The elongation of AB in the X direction, in the Y direction, in the Z direction, which we're not drawing here, as well as then you can look at all the shear strains as well, right? So, how much does AB, essentially shear, like move in the U2 direction with respect to change in U1 or change in X1, and you could basically work out through geometry all of the other components. Okay, I'm not going to do that because it would take up two more pages, right? But if you do that, ultimately what you get is that the strain tensor is equal to 1/2 partial UI partial XJ plus partial UJ partial XI. Okay, and again, if we look at what the 1-1 component is, right? Well, this is U1 X1 plus U1 X1, which is then 1/2 times 2 partial U1 partial X1, right? The 1/2 and the 2 cancel, and you get partial U1 partial X1, right? So we only derived this one. If you made those same geometric arguments for all of them, you would get this, and then we can verify that this reduces back to that for the 1-1 component, right? And it's because of this, right, these geometric arguments, that we need the 1/2 out front. And that's why we defined our Green strain and our Eulerian strain as 2E. Because we want those finite strain measures to collapse to the infinitesimal strain measure in the limit, right? If we linearize them, right? So we have these nonlinear strain measures. We want them to, if we what I'm trying to say is, if you linearize the nonlinear strain measure, you want it to collapse to the infinitesimal strain, because the infinitesimal strain we get to by making purely geometric arguments, right? Just thinking about how an infinitesimal cube would deform, right? And so, yeah, that's why we define it as 2E instead of just E, so that it would collapse to the infinitesimal strain. Okay? And remember, in the infinitesimal strain, there's no delineation between the current and reference configurations, right? They're just one. If the strains are small, there's just one configuration, right? The reference configuration. All right. Well, let's look at something that's interesting or perhaps flawed about the linear strain measure. Let's look at a cube, and this is going to be, we'll call this the X1 direction, X2 direction, and X3 will be out of the board. okay? So we're going to look at a cube here. And what we're going to do is we're going to just simply rotate that cube. So here's the rotated cube. It's rotated about an angle theta, and we'll call this little x1, little x2, all right? And so now what we want to do is we're going to write these vectors, little x1 and little x2, and of course little x3 is out of the board. Little x3 and big X3 share the same axis out of the board, right? So we're going to write down what these vectors x1 and x2 are in terms of the big X components, right? So we're just going to take the sines and cosines with respect to the angle theta, right? So if we write down the matrix equation, x1, little x2, little x3, in terms of cosine, well, cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1, and all this is multiplied by x1, x2, x3. Everybody okay with how I got to that? Basically just using the geometry. Writing x1 and x2 in terms of the big X1 and big X2 and the angle theta. So it's just a pure rotation. We're not straining that cube at all, just a pure rotation. Now, let's just imagine that these vectors are infinitesimal. That's an infinitesimally small cube. And these vectors are also infinitesimally small. So let's just put d's in front of them. So we have a vector equation then. I don't know why I'm writing in red. I'm going to change back to black here. Try to use red to highlight things, right? So d x1 equals something times d big X. So d little x times something times dx, right? Well, what does this equation look like? This is like our deformation gradient, right? What I say in words, the deformation gradient takes vectors in the reference configuration and changes them into vectors in the deformed configuration. Now in this case, those vectors are pure rotation. There's no elongation, right? It's just a pure rotation, right? So we might call our deformation gradient, so this is also known as a rotation matrix, right? And so in our case, our deformation gradient is just the rotation matrix. It's just a pure rotation, okay? So I think I better go to the next page for this so that the results will be. All right, so now let's write down the green strain in terms of the deformation gradient, which is also the rotation matrix, right? So the green strain is 1/2 F transpose F minus I, or since F in our case identically equals R, we'll write it in terms of R, 1/2 R transpose R minus I. Now, R is a rotation matrix, and all rotation matrices are unitary. You know what that means? Huh? It means that's one thing it means, but also it means that its transpose is its inverse. Any unitary matrix, the transpose is the inverse, right? So now I can write 1/2 R inverse R minus I. What is R inverse times R? I. 1/2 R times, so that's 1/2 I minus I, or the zero tensor. So, under a pure rotation, which makes sense, I didn't strain it, right? All I did was rotate it. Pure rotation gives me no strain if I compute the green strain. Let's see what happens if we do the same thing for the infinitesimal strain. So, and for the infinitesimal strain, we have 1/2 grad U plus grad U transpose. Okay. Remember we had this equation for F is equal to grad U transpose plus I. Remember we had that up here? Right here? So we can solve that equation in terms of for grad U transpose, right? So we can rearrange this equation so that we have grad U transpose equals to F minus I, right? So now, using this relationship, we can write our infinitesimal strain with the deformation gradient. Right? So we have 1/2 F minus I plus F minus I transpose, which is equal to 1/2 F plus F transpose minus I. Now let's plug in our rotation matrices. 1/2 R plus R transpose, because F is equal to R under a pure rotation. So when is this equation zero? When R is equal to I. Only when R is equal to I, right? So when R is equal to I, then I have I plus I. I transpose is I, right? I plus I, or 2I, times 1/2. So then this term becomes I minus I, and then it's zero. So it's only zero. So let me, what I'm going to say is that this is not equal to the zero tensor for any I, for any R not equal to I. So what that says is that if you have any rotation, your small strain measure is going to be wrong. Because it's going to say you have strain, right? This should be equal to zero. I didn't strain it. I just rotated that cube. I did not deform it. Strain is a measure of deformation, right? I did not deform it at all. So what this is saying is that for any rotation at all, you're going to have non-zero strain. So your undergraduate strain measure is always wrong if you have any rotation. And this, this is, think about a horizontal well, right? You start off, the drill pipe is perfectly rigidly straight, and stick it in, stick it in, stick it in, trip it in, trip it in, and over eventually you begin to bend it, and the strain in the pipe is very small because each section, bending over a long radius, there's not a lot of strain, but there's a lot of rotation. Like you're rotating at 90 degrees, and so if you were to use the small strain measure and try to model the entire dynamic tripping event, you would get a grossly wrong answer because you're rotating a lot, but you're not, but the strain is small. And what it would do is predict very large strains that are really rotations, right? And ultimately we use strain with a constitutive model to get stress, right? And stress is like a force per area, right? So that implies, like, if you have a large strain, then you're going to have a large stress, which implies large forces, but they're not really there. It's an artifact of the linearization of the small strain measure. And so this point is really the reason for this class, right? It's the reason for going through this exercise of all these finite deformations, so that you're aware. Like, there are many cases, many problems where the small strain theory is okay. It's good enough. It's a good approximation. But if you have any rotation, or, I think going back to the point I made on the first day or second day, like, what we call, that's why we say large deformation, because you can have small strains, but if you had, like, say, a long, slender rod, like a drill string, and you bend it, the strain can be small, but the rotation, the deformation can be quite large. And so you have to use the large strain theory. Okay? I'm going to go on. There's a little animation I made. I meant to pull it up before class so that it would be ready, and I didn't do that. And I actually don't know where it's at on my computer, so if I stopped right now and looked for it, it might take 5 minutes, and I don't want to do that. If anything, I can show it to you at the beginning of next class. So I'm going to move on now. We're going to talk about strain rates. And if there's time at the end of class, I'll show you. I'll try to find that. If not, I'll show it to you at the beginning of next class. Which it's just more demonstration of this concept.